Today we're going to talk about 7-3, triangle similarity, AA and SSS, which is angle, angle, and side, side, side. So from last section, we discussed when shapes are similar. And as a reminder, two things need to happen. The shapes need to have congruent corresponding angles, and you need to have proportional corresponding sides. In 7-3, we introduce some shortcuts for this. The three shortcuts that we can use to show that triangles are similar are angle, angle, side, 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 and side, angle, side. Today we're just going to talk about the first two, and we'll talk about the last one later on. Our first shortcut is postulate 7-3-1, angle, angle, similarity. It says that if two angles of one triangle are congruent to two angles of another triangle, then the triangles have to be similar. Just to demonstrate this postulate, we can look at triangle ABC and triangle XYZ. Now, if we knew here that, let's say, angle A is congruent to angle Y. So currently we have one angle of a triangle is congruent to another angle of a triangle. And we also knew that angle C is congruent to angle Z. Because of this situation where we have two angles in one triangle congruent, then we can conclude by saying that triangle ABC is similar to triangle YXZ. Notice I went in this order because of the corresponding sides. A corresponds with Y, B with X, C with Z. So let's go ahead and look at an example. What we want to do is explain why triangle ABE is similar to triangle ACD, and then find the length of CD. So we have our triangles here. We can start off with, first thing I notice is I see a right angle and a right angle. So I can say that angle ABE is congruent to angle, looks like ACD. And the reason for this is the right angles theorem. Now, what this theorem says, this was kind of one of our obvious theorems. It says that all right angles are congruent. That's easy enough. So we have two right angles and they're congruent by the right angles theorem. Do we have another angle that's congruent? Well, we have our little triangle here, ABE, and we have ACD here. Now, looking at this, it appears we do have an angle that's congruent, and it's right here, angle A. We know that angle A is congruent to angle A. Now I'm saying angle A and angle A because it's in both of the triangles. It's in the little triangle and it's in the big triangle, but notice it's the same exact angle. What's our reasoning for that? If it's the same thing, well, that's reflexive. It's like looking in a mirror. You're saying that the same thing is congruent to itself. So then why are they congruent? Or why are they similar? Well, we know that by angle, angle. So that's our explanation. This is what your homework should look like, is showing a few steps and stating why. Now that we know that they're similar, we can find the length of CD. How should we go about finding CD? Well, what we want to do is we want to set up a proportion. And this is because we know that these two triangles are similar. So let's talk about the bottom leg, because I noticed that we have a 9 and a 3, so we can have the bottom leg of both triangles. So let's do the bottom, which is AB, over the bottom of the bigger triangle, which is AC. Well, what is that? We know it's 9 over. Now, don't say 3, because AC in its entirety, AC is not 3, but AC is 12. That's 9 plus 3. So it's 9 over 12 will be equal to, again, we're setting up a proportion here, so 9/12 is equal to, well, we did the little triangle on top, so we're looking for DC. So we're looking for this length, the right-hand side of that triangle, so we need to look on the right-hand side of the smaller triangle, which is 5. So we can say that 9/12 is equal to 5 over the length of CD. And now that we've set up our proportion, it's just solving from here. You can cross multiply. 9 CD is equal to 60. Divide both sides by 9. And we see that CD is equal to 60 over 9. Or in a mixed number, this is 6 2/3. And now we are finished. Our next shortcut is theorem 7-3-2. Side, side, side similarity. Now we've seen side, side, side before, but that was when all the sides are congruent. We'll notice that this theorem is slightly different. If the three sides of one triangle are proportional, not congruent, but proportional to three corresponding sides of another triangle, then we know the triangles are similar. So looking at an example dealing with this theorem here, it says, explain why triangle PQR is similar to triangle STU. Well, let's go ahead and look at these and notice we're not going to use angle because we don't know any angle measurements. So let's deal with the sides then. Let's set up a proportion. It says that we have two similar triangles, hopefully, of PQ. Means that first, second. So let's set up a proportion with the first and the first and second. So PQ is 9 and ST is 6. This here reduces to 3 over 2. And I guess I should have written that this is PQ over ST. Let's set up another proportion, maybe now with the second and third and second and third. So we're going to do QR over TU, which is QR is 6, TU is 4, and this seems to reduce down to 3 over 2 again. Let's set up our last proportion with PR over SU, which we see is 6 over 4, which again reduces to 3 halves. Because all of these reduce to the same number, 3 halves, 3 halves, 3 halves, we can say that this is side, side, side. Because this means that, as side, side, side says, they are all proportional. And so therefore, yes, these are similar by side, side, side.